Good afternoon and welcome to today's webinar, JTAG-based debugging of AMD EPYC servers. My name is Heidi Richards and I'm the Director of Compliance and Continuous Improvement at Asset Intertech. Asset is the leading provider of ScanWorks platform for hardware validation and test and the SourcePoint platform for software debug and trace. Before we get started, I'd like to go over a few housekeeping items so you know how to participate in today's event. First and foremost, today's webinar should run approximately 40 minutes. During that time, you will have the opportunity to submit text questions to today's presenter by typing your questions in the question pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. You will also have the ability to participate in polling questions, so be prepared to participate. On that note, please be sure to download a copy of today's presentation, which can be found as a handout in the control panel of your screen. Now, without further ado, we will turn the time over to our presenter, Alan Squenya. Alan leads Asset's business development initiatives for JTAG, inclusive of debug, test, and hardware validation technologies, a prolific technical blogger, and author of the Middleboard Chronicles. In his spare time, Alan enjoys dabbling with x86 and ARM architecture and UEFI, Windows, and Linux kernel hacking. Over to you, Alan.
Thank you very much, Heidi, for the kind introduction. Hello, everyone. I hope everybody is ready for what hope to be an epic webinar. Sorry, that might be the last pun that I use today, but I'm quite fond of AMD's use of branding on the term epic. What we're going to do today is, in terms of an agenda, is go through a little bit of introduction to JTAG and its applicability for use cases in general and for debugging, particularly for this webinar. On AMD, look at the access mechanisms, right, that are supported for JTAG access and control. And then the emphasis is going to be on the SourcePoint application, right? So essentially a visual application used for firmware debug, very close to the hardware. And we have a demo lined up, where we'll see some of the things that you can do with JTAG and with SourcePoint, right, in terms of debugging, firmware, UEFI, core boot, building a type 1 hypervisor, and so on, with the actual application right in front of us. So, and then after the demo, we'll wrap up, and hopefully there'll be a bunch of questions that we can go through a Q&A on the back end. So JTAG is actually a very mature technology, right? I'm sure everybody on the call knows all about it, but it actually turned 30 years old back on February 15th, 2020. And JTAG is used as an access and control mechanism, to access engines or embedded instrumentation, within chips. And JTAG is ubiquitous. It's any chip of any size or complexity actually has JTAG in it. So it's literally in billions of devices out there, globally in all electronic systems. Very simple architecture, a state machine, a finite state machine, as in the top diagram on the right, drives the actual control. And behind every pin, most pins, there is a handful of gates, a couple of handfuls of gates, which constitutes a boundary scan cell, which allows serial access around the perimeter of the device, and parallel data in, data out access, through the pins, right? And so they mediate between JTAG, or the boundary scan cells and JTAG mediate between the outside world and the system logic inside of the chips. So as they relate to CPUs, there's a bunch of applications that have grown around, right, this simple and elegant technology over the last 30 years, right? Test, debug, validation, and programming. Today we're going to focus on the debug pillar. So and talk about what we use, what's called run control, right? The Intel in-target probe, the AMD hardware debug tool, and the ARM core site specification, right? These are the specifications that revolve around using JTAG in and out to access the debug logic inside of these CPUs. So why are we even talking about JTAG as a debugging utility? Why not use just OS-based, agent-based debuggers? Well, JTAG lives at the hardware. It actually lives at the interface between the the hardware, the firmware, and the software itself, right? And so if you're working at a very, very low level, right, and you need the most powerful debugging mechanism, out of band debugging mechanism, then JTAG is the way to go. Certainly, if the platform, if the system that you're working on is wedged, then JTAG is the only way in, right? An agent-based debugger becomes of limited utility at that point. And typically, because of its inherent nature, most of the silicon providers, Intel, ARM, AMD, all use JTAG as the access and control in early silicon validation before the firmware is even ready. So there's obviously some reuse and utility of being able to use the same control as what is used by your silicon supplier. And some people often express this application as hardware-based debug, JTAG-based debug, or hardware-based debug. Run control is typical things you hear what we call in run control: halting the system or halting the processor. Go, putting it in a running state again, setting a breakpoint, single stepping through the code. And often on any good debugger, sitting on top of the visual representation of these commands, halt, go, setting breakpoints and all, right? There's a scripting language or a command language sitting on top, right? A typical example, right, over on the right-hand side, right, that you can issue commands interactively directly on a command line with the platform, and even build in these command and control variables, right, into macros and use for regression type testing, right, or stress testing. The typical topology, and what you're going to see in the demo today, is the SourcePoint debugger. On the right-hand side is the actual application assets JTAG-based debugger. It can connect typically with either a USB or an Ethernet interface to a hardware controller, what our product being the ECM XDP3E. And that in turn is local and connected over JTAG and some sideband signals, the HDT interface with the EPYC server. And for the demonstration, we're working with an AMD Rome platform. It's a CRB, customer reference board, called the Ethanol X, people might be familiar with. All right, and before I walk to the next slide and jump into the demo, I'm going to hand it over to Heidi for a short bit for how about a polling question, Heidi?
Thanks, Alan. Our first polling question is, are you working on an AMD EPYC design now? Please select yes or no. Looks like a number of you have responded. Those of you who have not yet responded, go ahead and submit your response now, and we'll close the poll in a few moments. We are now closing the poll. It looks like 24% of you selected yes, and 76% of you selected no. Back to you, Alan.
All right, well, those are some interesting results, Heidi. Okay, about a quarter of us have actually had their hands on an EPYC server platform and doing some debug. Hopefully the rest will join the crowd soon enough. Anyway, continuing, for AMD, there's two primarily access mechanisms to the platform. What we're going to be seeing today is the SourcePoint example, whereby we connect locally, or sort of what I call on the benchtop, over the HTT plus interface, right? The header that's on the Rome server platform that we have. It is also possible to take the AMD run control firmware and embed it on a service processor. And that's via, for example, Asset ScanWorks Embedded Diagnostic, what we call SED product. AMD differs from Intel in terms of the main out-of-band access methodology for AMD is over a direct JTAG connection, a la HD Plus or via the BMC hardware connectivity to the CPU scan chain. Intel, on the other hand, has a fair amount of effort into supporting a USB connection over DCI, direct connect interface, which is fairly popular on the Intel side. But Asset itself supports the HDT Plus connection via that ECMXDP3E hardware probe. And SourcePoint, if you've ever used it in the past, you know that we cover both Intel and AMD on the x86 side. Really a visual source level symbolic some and support for multi-core, multi-socket, multi-processor, multi-thread. You'll see some demonstrations of some of this functionality right during the demo section in a minute. All right, and speaking of which, I'm going to get out of PowerPoint and switch over to, I actually pre-recorded the video for this demo because I'm very leery of Murphy's Law, right? We know how that goes for demonstrations. And I'm just going to do a voiceover on the individual features and functionalities of SourcePoint as I show them. All right, you should all be seeing the SourcePoint screen right now, and I'll be hitting play. And what we have, I'm actually virtual machining into a local copy of SourcePoint, right? That's directly in front of and hooked up to that Roam server I was talking about. This is an unlocked Roam server part, that we have here. It's on the Ethanol X platform, and so we don't use the Asset Secure debug unlock capability, right? This is just an unlock part, but we could if we needed to. The windows within SourcePoint, right? What we're looking at, what I'm highlighting here is the viewpoint window. Here we see all the processors, cores in this instance associated with this customer reference board, the Ethanol X. We have it's a 64 core platform. As you can see, we're in a running state, but some of the cores have been fused off. They're showing up as not active, and this was actually just characteristic of this particular platform. We're looking at core 0, the processor 0, the bootstrap processor right now, and because we're actually sitting in the UEFI shell. I've got a serial console here, right? We're sitting in the shell, right? I hit enter a few times, and just to show you that it's operational, you can type some of the shell commands to illustrate that we're in fact running live. And over here, I've got also have a VGA connection right into the platform as sort of a backup thing here. So anyway, you can see we're running. We had previously halted in the code window on the left. You can see we're in the shell. There's not a lot going on right now. So we're kind of in a sleep state waiting for something to happen. I hit that button at the top left. It's the stop button, and that stops the entire platform. It's a little macro button actually that halts all the cores, as you can see from the viewpoint window here, and changes them from a running state to a stop state. General registers window, right? You can see the general purpose registers here, and the ones in green are the ones that had changed when, from the last previous halt. So it tells you, very helpful in terms of seeing what's changed. And the ones in black are the ones that had not changed since the prior halt or the prior break. You can see where the instruction pointer is, same as what's showing up in the code window up there on the top left. And let's see, what else do I want to tell you about? Command window, can't forget that one, right? This is the way you interact directly with run control right? And some of the built-in SourcePoint command language, right? Macro capabilities. I can invoke, for example, the AX command shows hex 0, right? And if you look at the general registers window again over on the right-hand side, you can see EAX was in fact 0, and AX was 0 as well, of course. All right, the breakpoint windows here, I've actually placed a hardware breakpoint at the entry to Dixie main. You can tell it's a hardware breakpoint because it's in red here. And we're going to do some interesting things in terms of, well, first I'll show you that, in fact, the platform is halted, right? You can't hear this or see this, but I'm tapping madly on my keyboard, and things happening because the platform is actually in a halted state, right? Which is as you would expect. Right. So let's hit the go button and put it back into a running state. And let's look back at the consoles, all right? The console and see, okay, it's back and running, and those commands that we type are in fact, fully operational, right? Again, as you would expect. So we're gonna stop again because things get interesting, of course, when you're in a halted state insofar as JTAG is concerned. That's a reset button that we're going to hit right now. All right, so we're going to debug this thing directly out of reset, right? So we've initiated a hardware reset on the Ethanolix platform, right? We're waiting. It's take a few moments for the platform to reset itself. And wow, okay, it has stopped as you would expect. But actually, I've stopped in La La Land, as it were, right? I've actually stopped prior to the reset vector here. We're at what AMD calls in check 1. There's no code, right? We're actually not in the x86 world just yet, right? For some folks that might understand a lot more about AMD architecture. But you can see the instruction pointer from the general registers window is set to 17.710. Single step button here takes us to in check 2, which code FF, at the address 4F0093. Again, not much to see at this point. We'll take one more step, and that will take us to the reset vector, right? So this should be more familiar with folks that have done x86 debug on Intel platforms. In this case, 76.5F0, a couple of no-op instructions, right? Which we can single step through. And then we do that short jump over here and keep single stepping. And you can see from the general registers window, again, some of the applicable registers have changed value, right? As we step, one by one through the code. So easy enough to track exactly is what is going on, by looking at the general purpose registers here. We've got tooltips all over the place. Just by the way, I'm going to show you that I'll run to Dixie main now, right? So I'm going to click on the go button. So we're going to jump from the reset vector to the entry to Dixie main, and bang, you saw it really fast. You might have missed it, but we had a lot of text rolling off the serial console. And here we are. You can see in the code window that we have stopped at the entry point to the Dixie main procedure. There, the yellow bar and arrow is the instruction pointer, and the red blob on the left is where I placed the hardware breakpoint associated with Dixie main. So we're right at the entry point, and the tooltip shows you some good information in terms of addressing and the source path. And so as we ran through a lot of code going from reset to Dixie main, you can see all the general registers have been highlighted in green in this instance. All right, I'm going to show a little bit now about what you can see on AMD in terms of what JTAG run control brings to the table, right? In terms of capabilities that you can use in terms of managing, all of the registers, right? All of the architecturally visible registers on AMD platforms. hover over the value of a register, and you can see the tooltip. In this case, the subfields associated, with the registers, right? And the EFlags register is the most interesting one in terms of the number of available subfields there. And you can also right-click if you wish and expand, right, on the contents of the registers and click any of the ones, change them in any way you see fit. If you want to, very helpful, for example, in debugging process, escaping a dead loop or whatever. We've got access to the floating point registers, the segment registers, right, and so on. Debug, all of this is very similar to Intel. There are 4 hardware breakpoints, available on the AMD platforms, the same as Intel. Many more software breakpoints available, of course, on the platforms. And for the MSR, we've actually imported the contents of the publicly available MSR documentation, right, our own platform. So you see here the name, value, address or number, and then description, right? So it's easy enough to find what you're looking for. And again, the ones that have changed since the prior break are highlighted in green, and all the rest of them are in black. We've got access to memory typing, the machine check, and so on and so forth. Secure virtual machine, right? If you're doing some work debugging the memory encryption technologies and so on. All right, back to the code window for a second. Just want to show we're looking at the code, right, in source view, as it were, right? And we can see where this particular, the Dixie main procedure lives, within Dixie main.c. We've got all the source and symbols loaded on, associated with the UEFI image on this platform. You can scroll through and look at stuff as you wanted to, and look at the tooltips associated with the variables and all. You can also look at the code from a mixed perspective, which intermixes the C code itself and the associated assembly. This is the way I typically like to work myself, like to see both. Or if you're really hardcore and don't really need to look at C code, there's the assembly language directly available to you as well. You can single step, of course, in any of the modes. If you're in assembly language mode, you can single step, right, and go from one assembly instruction, to the next. If you're in C code or in mixed mode, right, you can use the step over or sort of buttons there right beside this, the step-by-step ones there if you're debugging, at a source level, right, as opposed to the assembly language level. All right, let's see, breakpoints. Let's go back into in the mix mode, and let's look at breakpoints for a minute, right? Because this is really the trade, right, of the professional debugger, right? With SourcePoint on AMD, as with Intel, you have a plethora of different types of break that you can initiate, as displayed here. You got available 4 hardware breakpoints and over however many software breakpoints available to you. And when you hit a break that you've defined, you can initiate a command or a macro there at the bottom, which allows for the which allows for regression testing or running an algorithm after you've actually hit the break. So you can put those breakpoints in the via the breakpoint window, or you can do it from within the code window itself, right? So you have a choice, right? The latter might be more convenient, and the easy way to do that is set a line of code that you're interested in, set a break, which will appear at the next available instruction. And when we have that green blob, we can toggle from software green blob, hardware red blob, essentially, by toggling the breakpoint type, via right click and select. Of course, there are keyboard shortcuts for any of those. All right, so let's hit the go button, and bang, of course, we jump from the entry point to Dixie main and just a little bit further down, right, into Dixie main at the alloc runtime copy pool. And jumping back over to the general registers window, you see the contents that had changed. I'm going to take a short break now and take a little bit of a breather here. And so I'll hand it over to Heidi for another polling question.
Thanks, Alan. Our next polling question is, I do my firmware debugging mostly with printf, AMD HDT tool, asset SourcePoint tool. I don't do debugging. Please select one. It looks like 57% of you have voted. If you haven't had an opportunity to vote, please do so now, as I'll be closing the poll in a few moments. I will now be closing the poll. It looks like 31% selected printf, 25% selected AMD HD tool, 38% selected asset SourcePoint tool, and 6% selected I don't do debugging. Back to you, Alan.
Oh, thank you, Heidi. Appreciate it. Interesting results. All right, let's continue. The next thing I want to show is the functionality inherent in inspecting memory within SourcePoint. You click on the memory button at the top, and you can see inside the window that you've got a number of different ways that you can specify the specific memory that you're looking for: linear, physical, segmented, offset, or even symbolic, by hitting the magnifying glass and browsing through the symbol library. And I'll show that in a minute. Let's see, we're going to put some memory in here to have a look at and show what that window looks like. I'm gonna, just for grins, I'm gonna pull out the instruction pointer contents and go back open the memory address window, copy and paste that in, and you see the memory window here. All right, a lot of different ways you can customize the view. We're looking at 8-bit right now. You can specify 16-bit, 32-bit, 64-bit if you're looking at the contents of double words or whatnot, and specify how you want to see any associated text or character, ASCII or Unicode. Nothing much to see here right now because I'm just looking at code, right? I copied and pasted the instruction pointer in. All right, let's have a look at some of the powers of source level debug associated with SourcePoint. So I'm back in Dixie main again at the entry point where I place that hardware breakpoint right at the beginning. And I've also put a software breakpoint. If you look carefully at the breakpoints window down below, you'll see that I've got a software breakpoint at core install configuration table plus hex 18. All right, so it's a little further down that procedure, and install configuration table is invoked a handful of times from within Dixie main, actually. And what it does is it updates the EFI system table configuration table, right? With contents. Clicking on symbols shows me a little bit of what we can do with that power. Looking at globals, locals, the stack, or the classes associated with the image, you can see we've got a rich set of contents here, right, associated with, for example, right, just one name, the data, labels, and so on, all the function names, right, the modules themselves associated with the globals. Here's what's local to the main, of course, where the locals that are available as of that in the instruction pointer. If you want it, you can also get some more information. And in addition to seeing the name and value, you can look at the address and the actual type, right, of that symbol. Those symbols. That's what's on the stack, and there are the classes available, with the structs, that are accessible therein. let's display some of the power and the functionality of symbol search. Right, so you right click right in any of these windows, any of these tabs actually, and using the find command, you can look inside the code, right, inside the data within the image, the modules, right, for particular strings. And you've got a lot of control over what you're looking for, like starting with, containing, wildcard pattern, or even putting in a regular expression. And you'll see how fast it is actually, because as you can imagine, there's a lot of symbols right inside this image. I've got a start string. Oh, I'm really looking for core install something, and you can see I found 4 instances of it here. Let's move this over a little bit so you can see, right? One of which is my core install configuration table function. And if I wanted to, right, I could open a code window associated with that symbol, with that function, set a breakpoint, and so on. A lot of few things that I can do. So that's pretty much what I want to say about symbols, right? Let's get into some source level debug fun then. I've got the set, as I had mentioned, right? Software breakpoint inside of my my core install configuration table routine, and I'm going to, let's see, I think I want to make a jump from where we are, right, in install configuration table. But looking at the code inside the Dixie main, let's find that routine first so we can see exactly what's going on. All right, I went too far. There we go. First invocation is installing the Dixie services table, right? And then we do the hobs, and then we do the memory type information table. So we're gonna go and hit the button, and once that we jump to that point, right, it'll be the first invocation since farm had been reset of core install configuration table. And there, it happened so fast you might have missed it actually. Or you can see I've actually stopped. The instruction pointer is now at hex 18 down from the start of the function routine start. I've got a couple of parameters coming in, pointers to GUID and table here. And let's see SourcePoint's symbol capability, right? Let's copy that variable, right, that pointer into a watch window. In fact, I've already taken the liberty of copying both table and GUID, right, the 2 income parameters to a watch window, and you can see the values associated with each on the initial entry point. If I hit go again, right, it's going to run out of core install configuration table, go back into Dixie, and get to the second invocation of the core install configuration table. And it did actually. I hope you saw that. But second time in, and that's when we're installing the hobs list right into the EPYC tables configuration table. So anyway, hopefully that has been helpful, an easy demonstration, just what you would get, with the, for example, Visual Studio type of debugging environment, but at a very low level and using JTAG. All right, I'm going to wrap up the demonstration now with a look at what we have in terms of and some of the power of the command language, right? The macro language that we have available. Under the help menu, click on index, and you can search, right, a ton of information in terms of indexing or searching terms or looking at the table of contents. Let's look at the go command. Let's take that one as an example for short, right? The go command. It's not just go and stop, right? It's actually a command with a bunch of possible parameters. You can prefix it with a P0, P1, P2, the actual processor viewpoint, the processor that you want the go command to operate on. And then there are a bunch of parameters as defined below. You can go forever, go to a software breakpoint, address, event, and so on. And all of the documentation, of course, has some good examples on the back end, for each of these commands, right, that allow you to, understand exactly how to use the function. To illustrate, I'm going to show how the go command that can be used to actually run the target and then halt it. I hit go in the command window, and well, I didn't actually have to hit stop because we jumped from the breakpoint that was in the first invocation of core install configuration table to the second invocation of core install configuration table. As you can see, we're at the software breakpoint again, right, as we were. Let's get a little bit more complicated and use some of the parameters. Go till 80 IO. That means it's going to run the target until it hits the next port 80 read or write. And if you glance back up at the code window now, you'll see, okay, the source actually changed. Let's put this in mixed mode so we can see it a little bit better. But the instruction pointer, the yellow bar, is just one instruction down from the out instruction of EAX, right? The AX register, which is contains C38, as you can see from the general registers window. And that was copied into the contents of DX, right? Which is hex 80, port 80, all right? And we broke out instruction. We could also, even more powerful, right, put conditional logic in here and put that to use, do a while one, which can go forever. And we're going to run until the next port 80, read or write, and then we're going to wait, and then we're going to display the AX register contents at that time, and just keep going forever. As you can see here, it's updating, the code window is updating in real time, viewpoint, general registers window, all updating in real time. And I canceled it since it would go for a fairly long time. But you can see just with one simple command, command string, as it were, initiated on the platform, you can do a lot of really cool things. Documentation, if you really want to, you don't want to use the help files, online files, you can crawl through 645 pages of documentation associated with our user's guide. This is actually how I prefer to consume, read content, sit on the couch and go through a book from beginning to end. Plenty of information, well written, easy to understand. What's all of the basic functionality associated with the GUI. Half of the 645 pages is associated with the GUI itself, right, and the capabilities of SourcePoint as you've seen it so far. And the other half of the documentation is a description of the command language, right, the macro language. Very instructional. I'll show you an example actually of the command language itself. We've got macro buttons defined at the very top of the under the title bar for SourcePoint, and like autos are associated with macros, right? That you can write yourself or use the built-in macros built into the application, right? There's the macro button at the top that dumps the hobs, and just hitting that button invokes this macro. And you can see the command language, the macro language is very C-like. So if you're a C programmer, you know something a little about x86 debug and UEFI. This should be fairly simple, easy to understand, and to code up your own applications easily enough. All right, I think that pretty much with the demo. I'm going to pause again for another polling question, Heidi.
Thank you, Ellen. Our third and last polling question is, the firmware I'm working on has 0 debugs, not many bugs, a lot of bugs, so many bugs, I'll never get to them all. Please select one. Looks like 59% of you have voted. So if you haven't had an opportunity to vote, please do now, and I'll close the poll here in a moment. I'm now closing the poll. The poll results are 8% of you have 0 bugs, 33% not many bugs, 50% a lot of bugs, and 8% so many bugs I never get to them all. Back to you, Alan.
I like that last answer, Heidi. That's the best one, I think.
It is.
Anyway, for any more information on this topic, by all means, you've got some content on our web, our SourcePoint AMD page. Yeah, you can have a look at a little bit even more comprehensive or broader presentation on JTAG-based UEFI debug and trace that we did in partnership with the UEFI forum last year. And that recorded webinar is available on YouTube at the link there. Of course, you can get these links from the handouts. Still in GoToWebinar, right, in your control panel. And then finally, we have an upcoming UEFI webinar. We're given kind of equal time between AMD and Intel, right? We're going to talk in detail in another demonstration of Intel architectural event trace, which is an event trace capability, that exists within within Intel silicon, which is pretty powerful, and that you can register for at that link down below. And if you still have some burning questions beyond that, feel free to contact me, please, at my email address is often the best way to get in touch with me. All right, I think that's it for the demonstration and presentation. Heidi, do we have any questions?
We do. Thank you, Alan. We're now going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions through the questions pane in your attendee control panel. Alan, our first question is, are AMD Ryzen CPUs supported as well as EPYC?
Oh, good question, actually. Yeah, good question. Currently, our support is on the EPYC side only. Well, EPYC and Threadripper are the other two CPUs families that SourcePoint supports. Ryzen support on the client side, notebooks, laptops, is in the planning stages.
Okay, thank you, Alan. The next question is, could you summarize the main differences between debugging on AMD and Intel CPUs?
Yeah, certainly. Both platforms are very similar, right? A lot of what you saw today on the EPYC platform, on the AMD platform, is common with both Intel and AMD. The main difference is really between the two platforms from a debug or a JTAG point of view is that the Intel has a number of trace features that EPYC lacks. What you saw today is primarily run control, right? There are some nominal trace features available on AMD, but nothing to the extent of architectural event trace, for example, right, or Intel processor trace. Also, Intel has the direct connect interface or DCI capability, sometimes called DBC debug class, that allows you to go in, over a specialty debugging USB specialty cable and do debug that way, right, as opposed to going in from an open chassis approach, right, via the HDT plus header.
Okay, our next question is, are SMM entry and exit breaking points supported?
SMM entry breakpoints are supported on AMD. The SMM exit breakpoints are not supported.
Okay, another question we have is, can you show port 80?
Absolutely, absolutely. Well, there's several different ways you can do it. Actually, when I ran that macro command, via the command line, I I did an output of the AX register, for example. So every time we hit the port 80 breakpoint, which was inherent in the go till 80 part of the command, right? We popped out the value of AX, which is essentially, what was the port 80 contents, right? At any other arbitrary places in the code, you can actually go in and via the command language, right? There's a port command or a deport command, right? That will display the whatever you want, right? In terms of a register contents or the port 80, whatever port you want contents.
Okay, we have two last questions, and they come in back to back. So can you show a dump of memory, presumably via physical address?
Yes, I can. We don't have the target live now, but yeah, you can do a dump of physical memory, for example, via the memory window. If you're using the interactive, kind of the visual aspects of SourcePoint, right, and suffix it with, for example, the P instead of the L, if you wish, depending on where you are in the code. Alternatively, again, with the macro language, because the GUI itself, the visual aspects of the tool, right, as well as the command language are very intertwined and dependent upon each other, right? So you could actually do a dump via the command window, the command language, right, if you wished.
Okay, and our last question is, can you show reading and writing to memory?
Yes, I can, but not now. Yeah, what you simply do, for example, the same approach, right? In the memory window itself, click on the byte or word or double word that you want, right click, and then edit, right? Very similar, the same approach that I showed for how the general purpose registers can be edited. And again, via the command language, right? The mem command, I believe, is the one that you would invoke to read batches of memory, right? System memory, DRAM, for example, right? And then make the appropriate changes. All of that's documented. The specific syntax, parameters, and all are documented inside the command language description.
Okay, perfect. Well, it looks like we're running out of time, Ellen, but is there anything else you'd like to cover or, before we wrap up?
No, that's it. I think, thank you very much, Heidi. And again, anyone, if there are any other unanswered questions or anything else that anyone wants to know about SourcePoint AMD, feel free to drop me an email.
Perfect. Thank you, Alan. And thanks everyone for attending today's webinar, JTAG-based debugging of AMD EPYC servers. If you have any other questions, please be sure to make a note of Alan's contact information listed on the last slide of the presentation. As you exit today's webinar, we'd appreciate it if you'd complete a survey on the presentation and provide your feedback. You will also receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. On behalf of Asset Enertech and our presenter, thank you for joining us today and have a great rest of your day.